evidence of massation is taking place due to the passage of a projectile carrying an unbalanced electric charge. For alpha particles, the electrical unbalance amounts to two positive elementary charges. Today, we are going to see how Ernest Rutherford used alpha particles to investigate the structure of the atom. Rutherford knew a good deal about the alpha particle. He had measured its mass. He had measured its electric charge. As a matter of fact, he had determined that an alpha particle is a helium atom without its balancing negative charge, its two electrons. He had measured the velocities of alpha particles ejected from radioactive elements, and it was after he had observed alpha particles passing right through gases, liquids, even metal foils, and knew how to count them, that he realized that he had at hand a tool with which to explore the inner structure of the atom. Let us look a little more closely at these atomic probes, these alpha particles. This time, we will use a cloud chamber of different design. Our radioactive source is polonium, and it is held in place by the screw on the left. Beyond the alpha particle tract, you can see a small wire scale that we have laid on the bottom of the chamber, and against which we can judge how far the alpha particles travel. Notice that the longest tracks go out about 4 divisions on the scale. Now we can set up a barrier across the path of the alpha particles using a metal foil. This is gold foil, similar to that Rutherford and his assistants used. It is very, very thin, only a few thousand atoms thick, and it's hard to handle. Nevertheless, we've managed to get our cloud chamber fitted with its barrier. You see it here as a fuzzy light line across the face of the source. The alpha particles pass right through it. To look at the tracks, you'd think the gold foil was not there at all. The particles go through it with ease. But there is a little difference showing up. Distance. Now the longest tracks go out only about 3 divisions on our scale. They don't seem to travel as far. The foil has reduced their energy, slowed them down a little, and they are consistently stopping short of their former range. There is another effect that the gold foil has on the alpha particles that we cannot see just by examining these wispy tracks by eye. The tracks are ever so slightly deflected, rarely by more than 1 degree. Rutherford suggested a study of this deflection to his colleague, Hans Geiger, who was already on the way to perfecting the now famous Geiger counter. This is how Geiger proceeded. At one end of a glass tube, evacuated, and about 1.5 meters in length, his radium source. Partway down the tube, he placed a slit to give him a narrow, well-defined beam of alpha particles. At the other end, he placed a scintillation screen. He used a microscope to see the flashes produced by the alpha particles as they hit the scintillator. When he used gold foil, he placed it over the slit. With this equipment, he recorded the distribution of alpha particles, with and without the gold foil, and prepared a graph of his findings. Here is the center of the beam of alpha particles, 0 degrees. These figures represent the angles of deflection of the alpha particles in degrees, and of course the vertical coordinate represents the number counted. This is the beam as he saw it without any gold foil present. You can see that it is only 1 degree wide and had very sharp edges. This second graph shows the effect of the gold foil. The beam fuzzed out at the edges. About half the particles were deflected through 1 degree, a few to 3 degrees, but none beyond 5. The equipment for our demonstration is arranged a little differently. Our polonium source is on a rod here in a cylindrical brass tube. Here's the aperture through which the alpha particles emerge, and we have made our aperture quite large so that a great number of particles will pass through the gold foil in a short period of time. Where Geiger's beam was about 1 degree wide, ours is, in fact, about 70 degrees wide. The gold foil is here, and our electronic detector is here, and is movable in an arc about the gold foil. Since we are not using a vacuum, as Geiger did, our components must be grouped closely together. This is the tube containing our polonium source. Here's the thin gold foil, and here's the detector we will use to count the alpha particles that penetrate the foil. It's a brand new device made out of a transistor. It gives a sharp electrical impulse as an alpha particle hits it. Here, it is connected through an amplifier to an oscilloscope and a loudspeaker. This arm pivots, letting us move our detector in an arc across the beam of alpha particles and out of it on either side at any angle. Our detector is light sensitive, so we'll place a shield over it and read its angle by this marker. Now we'll switch on the amplifier and hear a snap from the loudspeaker for each alpha particle. We also see a pulse on the cathode ray tube. Even though we are working with a much broader beam of alpha particles than Geiger did, we can still see on our counting equipment the rapid fall-off at each edge of the beam. Here are the alpha particles, about 500,000 per second in the beam. The beam goes from here over to here, diminishing rapidly, and we'll mark this as the edge of the beam. And the same way on the other side. Here they diminish rapidly, and we'll mark this as the other edge of the beam. And now if we go beyond, we find none. Perfectly quiet. None of the alpha particles are deflected more than a few degrees from their original direction. What was that? A count? At this angle, that's 25 degrees out of the beam. There's another. That was 3. Is the gold foil really responsible for these counts? Let's see. Silence. Now let's put the gold foil back. Now the gold foil is back in the beam of alpha particles, and we'll wait and see. There's a count already, 2. This wide-angle scattering seems to be caused by the presence of the gold foil, all right. What is going on? This is what Rutherford wondered when a discovery of these wide-angle scatterings was first made by Ernest Marsden, a young graduate student under his direction. Marsden found that on the average, about one alpha particle out of every 8,000 was deflected through more than 90 degrees. What was there about the structure of matter that would give rise to such violent changes of direction for a few alpha particles and scarcely any for the vast majority? Here is a model that will enable us to examine this problem more closely. These steel ball bearings will represent alpha particles. The ramp will launch them with uniform energy. This, of course, represents our gold foil. Now let's launch some. There goes one. These hot ball bearings leave tracks as they cross our specially prepared waxed paper. There's a fourth and a fifth, but this one was deflected through a large angle. Two more, straight. Another one, straight. Another straight. Another straight. And another one. We have set off 11 in all. Of the 11, 10 have followed the kind of course Geiger observed, but one has undergone a large deflection of the kind that Marsden observed. Let's run out about 200. Now we have our sensitized paper record about as full as we can make it. How did we make out? How many violent collisions? 1, 2, 3, 4, 5, 6. These points in our gold foil look suspicious. Let's see what's there. Aha, hard steel fins. No wonder the balls bounced. Our model gold foil is not really uniform in structure. It consisted partly of fuzzy felt space through which our so-called alpha particles penetrated with ease, and partly of small, massive scattering centers. This sort of possibility is what Rutherford guessed at. He knew that atoms were full of electricity. Ionization, electrolysis, and so on suggested that atoms had lots of electricity in them, despite their being electrically neutral when undisturbed. And he knew the negatively charged electrons were very light compared to the mass of their atoms. So he proposed that all of the mass of the atom, except the little part belonging to the electrons, might be concentrated, really concentrated, in a minute space at the center of the atom, leaving the rest of the atom empty, except for the light electrons. Then, if this massive core were to carry a large electrical charge, the electrostatic force between this charged core and the charged alpha particle might explain the wide deflections. Now, if this view of the atom were true, how could it be checked? Rutherford turned to the very deflections that had created the puzzle. He would make an accurate record of the deflection angles tell him what kind of collision had taken place. Can you tell from a series of collisions what force is responsible for the deflections? Do you remember the toy train cars? They made a collision at a distance because of the forces of repulsion between two magnets. For magnets not guided by tracks, a magnetic deflection looks like this. Or this. You can see the angle of incidence and the angle of emergence. Sometimes that's all you can see. But a study of the angles of deflection can often tell us a great deal about the nature of the force that produced the collision. Here's another collision you are familiar with. It is often called a hard sphere collision. Nothing happens until the spheres appear to come into contact. Now this is a type of collision you may not have seen before. This is a very light, dry ice puck. It seems to be working all right. And this is a small Van de Graaff generator. Let's switch it on. When it's charged up, it has a large positive charge. Now let's share the positive charge on the Van de Graaff sphere with the sphere on the dry ice puck. When the two spheres are charged, they have the same type of charge, and they repel each other with a Coulomb force, a force which varies inversely with respect to the square of the separation of the two spheres. Now let's see an electrostatic collision. There was a wide encounter and a deflection angle of about 45 degrees. Now let's charge the sphere again. It gets hot to handle by hand. Let's try a more direct encounter. There it goes slowly in and deflected almost directly backwards. A deflection angle of about 150 degrees. Now let's charge it again. And see another encounter. Each of these encounters shows a deflection angle that's connected with the encounter distance in a way characteristic of the electrostatic force. Let's charge it again. That encounter produced about a 90-degree deflection. We have seen three types of collisions: magnetic, contact or hard sphere, and Coulomb or electrostatic, and the types of deflections each produced. As a matter of fact, any type of force at work in a collision produces its own characteristic deflections. Rutherford strongly suspected a Coulomb type interaction rather than magnetic or hard sphere or any other kind. So he set about calculating the deflection pattern that his positively charged, minute atomic core would produce. Using Coulomb's law, he deduced the angles through which the alpha particles would be deflected as a function of how directly they were aimed at the center of the atom. Square at the center, an alpha particle would turn through 180 degrees and come right straight back. If it approached a little off-center, as this one does, it would be deflected through a large angle, say 125 degrees, and come out here. Another one, approaching a little further off-center, as this does, will go through a lesser angle and come out here. Another one approaching still further out, like this, would come out here. And another one approaching way out here would only be deflected by the Coulomb force through a small angle, say 45 degrees. Each of these trajectories and all the intervening paths Rutherford found to be hyperbole. And it isn't just in this plane that these trajectories occur. They occur all about the nucleus of the atom, in this three-dimensional space. Here's a hemisphere that will help us picture the directions along which the alpha particles fly away from the nucleus after being deflected by the Coulomb force. And I will ask you to picture another hemisphere under the table, for everything that I say about angles on the upper hemisphere will apply equally well to the lower hemisphere. When Rutherford was satisfied that he understood how each individual alpha particle would behave under the influence of force, he turned his attention to a calculation of the fraction of the alpha particles that would emerge at each angle. That is, how they are distributed as they come out. From this direction, we can imagine a uniformly distributed rain of alpha particles. An alpha particle that falls at this point on the rim of this smallest circle will follow a trajectory indicated by this wire, go in toward the center of the atom, and emerge along this direction. One striking the same circle at another point, say here, will go in toward the center and come out along this direction. In fact, particles striking anywhere on the rim of this circle will come out in directions like this through this arc. And I'll draw the arc. In a similar way, a particle entering the Coulomb field here, at this point on the second circle, will go in along this trajectory and go out along here. In the same way, all around this circle. And I can draw an arc to represent the places where alpha particles with exactly those trajectories will emerge from the nucleus. And for this third circle, the particles will fly out at angles through this arc. Lastly, particles approaching somewhere out here will emerge through an arc along here. Now we have the spherical space about the nucleus of our atom, marked out with certain limiting arcs which are determined by the trajectories we established before. In fact, each of these circles is directly related to each of these arcs. For instance, all of the alpha particles approaching the nucleus within this inner circle will come out at angles greater than those approaching right at its rim. That is, they will come out through this cap zone here. Now you can see that alpha particles entering outside the inner circle, that is, through this annular ring, which I can mark, will come out through this zone. In other words, each pair of arcs marks out a zone of emergence that is directly related to each pair of circles in the approach area. Particles going in through this annular ring will come out through here, and particles going in through this largest annular ring, which I will mark, come out here. So now we're able to tell exactly where the alpha particles go. That is, at what angles they emerge. And in fact, we can also predict the quantities. For the quantities going in through each circular area are exactly the same quantities that come out through the corresponding zone on our sphere. Now let's think about the experiment. To take counts in an actual experiment of this type, we have to have a detector. And on this scale, the detector will be way out there. For you remember that this model just represents the minute core or nucleus of the atom and a little of the atomic space about the nucleus. For the purposes of argument, let's assume that all the particles that come out through this square on the spherical surface will hit our detector. And that's true not only at this position, but at any angle on the sphere. So our detector always sees a fixed fraction of the total spherical space about the atom. Can we arrange it so that our detector also sees a fixed fraction of the alpha particles coming through each zone? We can do it by choosing the areas of the zones to be equal. How do we do that? We do it by selecting the trajectories which divide up the zones. In our particular case, we wanted 4 zones, so we chose 4 trajectories that would make the zones have equal areas. This means that our detector always sees a fixed fraction of the alpha particles coming out through each zone. So if the number of alpha particles emerging from one zone differs from the number of particles emerging through another zone, the fractions striking our detector have the same ratio. So we have a uniform rain of alpha particles passing through concentric circles of various sizes, but emerging through spherical zones of equal size. Now look at this. All the particles which go in through this inner circle emerge through this cap zone, and those that go in through this outer ring emerge through this 4th zone, and you can readily see that the number of particles that will go in through this outer ring is much larger than the number of particles that will go in through this small inner circle. So the number of particles emerging through this 4th zone and going out to the detector will be much larger than the number of particles that goes out through this cap zone and into the detector when it is out here. So the key to our problem is the relative size of those input areas. With a uniform rain of alpha particles, the number entering the inner circle, or any of the annular rings, is going to be directly proportional to the area of that circle or ring. So now we can write that the number, capital N, striking our detector is proportional to the input area, A sub I. Now let's prepare a graph of the way we expect the data to appear. We will let the vertical axis represent the predicted number of counts, and the horizontal axis will represent angle, and will extend from 180 degrees to 0 degrees. We will let the number of particles that goes in through the inner circle and comes out through the cap zone into the detector be our unit number. And the cap zone extends from 180 degrees to 125 degrees. So on our graph, that portion looks like this: 180 degrees to 125 degrees at unit number. Now the first annular ring is 1.8 times as large as the inner circle. So 1.8 times as many alpha particles will pass through it and out through the first zone as went in through the inner circle and come out through the cap zone. That zone extends from 125 degrees to 98 degrees, and the count is 1.8. So that portion of our graph will look like this. The second annular ring is 3.7 times as large as the inner circle, so 3.7 times as many alpha particles will pass through it and out through its corresponding zone. This is 3.7 here. And the angular extent of that zone runs from 98 degrees to 74 degrees. So this portion of our graph will look like this. Finally, the outer annular ring is 15 times as large as the inner circle. Therefore, 15 times as many particles will pass through it and out through its corresponding zone as pass through the inner circle. 15 is up here, and the angular region of that zone is from 74 degrees to 45 degrees. So that portion of our graph will look like this. And now the character of the scattering pattern becomes apparent. You can see that far fewer alpha particles are scattered through large angles than are scattered through small angles. Now we have taken this calculation in large angular steps. If we had more time, we could have taken smaller steps and more of them, and we would have had a curve that looks something like this. You can see that the number of alpha particles varies continuously with angle, instead of being averaged over large angular intervals. Now there's a great deal of approach area out here in the atom, much more than the area we've considered near the nucleus. So most of the alpha particles in the rain hitting the atom go almost straight ahead, as Geiger had first seen. Those alpha particles that are only deflected by a degree or two would be plotted here on our graph, and there would be a great number of them. This part of the graph shows you the kind of scattering pattern Rutherford expected Geiger and Marsden to find at the larger angles. Here we have a carefully prepared graph based on his calculations. As before, the predicted count is plotted on the vertical axis, and the angle of the detector is plotted on the horizontal axis. Here, by contrast, we have a graph derived in a similar way for hard sphere scattering. And here is the curve you would expect if the deflecting force were proportional to 1 over r cubed instead of 1 over r squared, as in the Coulomb force. You can see that the three curves are different. Each curve provides a signature or fingerprint of the type of force that is at work in the collision. By February of 1911, Rutherford had prepared the curves for the electrostatic case. Within a few weeks, he had completed for publication a description of his nuclear atom model with the prediction that the scattering force was electrostatic. Then he set Geiger and Marsden to work at an experimental confirmation, which we could approximate with our apparatus. For each angular setting of the detector, the rate at which alpha particles struck the detector was carefully recorded. Work which took them months, we can do today in hours with our modern accelerators. After 18 months of painstaking effort, the scattering pattern Rutherford had calculated was decisively confirmed. Geiger and Marsden's counting rates, plotted against their counting angles, fitted the curve characteristic of the 1 over r squared Coulomb force. Their data did not fit the curve for hard sphere collisions, and it didn't fit the 1 over r cubed curve. To be even more certain, they did experiments with foils of metals other than gold, and with alpha particles of different energies. And they all fitted with the prediction of a 1 over r squared Coulomb force field within the atom. Rutherford's extraordinary piece of deductive reasoning had given the world an entirely new concept of the structure of the atom. For the first time, it was seen as a sort of a minute solar system, with the nucleus as sun, carrying virtually all the mass of the entire system, with the bulk of the volume being empty space, permeated by intense electrical fields, and with the electrons distributed in this space, balancing by their negative charge the positive charge of the nucleus. Did Rutherford come to any conclusion about how small the nucleus actually was? He did. For even the alpha particles which approached the nucleus most directly scattered as he predicted they would under the influence of a pure Coulomb force. And his calculations showed that the distance of nearest approach was less than 10 to the minus 11th centimeters. In an atom, which is 10 to the minus 8 centimeters in diameter, this charged massive core must be concentrated in a space which is smaller than 10 to the minus 11th centimeters. We can hardly see that on this scale. Let me give you an idea of the amazing image this creates. Let us suppose this point of light, 1 millimeter in diameter, to represent an atomic nucleus. I'm going to place it here. And then I'm going to ask you to back away from it. Further. Further still. There. From there, you should be able to see the whole of this circle. It's 3,000 millimeters in diameter. And on the scale of this model, it represents the outer dimensions of the atom. Now I'm going to take another point of light, also 1 millimeter in diameter, and let it represent a helium nucleus, an alpha particle. Is it any wonder that most of the alpha particles travel through the gold foil as though it were empty space? But it's a peculiar kind of empty space. Its outer dimension is as unassailable as the Greeks said it was. With all this space, why doesn't matter collapse? Why don't the charged particles of the other atoms move into this space? Another 20 years passed before that question was answered. That answer, and everything else we know about the atom today, are firmly built on Rutherford's triumph with its brilliant analysis of the force, mass, space relationship of the atom.